Recent reports from China indicate that CL, currently the largest battery manufacturer in the world, has unveiled a new generation of sodium-ion batteries with a staggering 200 kilowatts charging capability. This development marks a significant leap in battery technology and could have profound implications for the electric vehicle industry. Sodium-ion batteries, once seen as a potential but limited alternative to lithium-ion technology, are rapidly emerging as a viable competitor due to their lower cost, faster charging capabilities, and steadily improving energy density. The new battery pack from CATL appears to be an upgrade of its free void design, which previously combined sodium and lithium cells. However, indications suggest that the latest generation may rely entirely on sodium cells. The charging rate of 200 kilowatts or 12C represents a level of speed that was previously considered unattainable. This kind of performance has the potential to disrupt not only the battery market, but also the broader electric vehicle industry, as such advancements drastically reduce charging times, improving the convenience and viability of electric vehicles for mainstream consumers. CL is not alone in driving this innovation. Other major players in China, such as BYD, are also advancing at a rapid pace. This puts battery manufacturers in South Korea and the United States under increasing pressure to keep up. The pace of development in China is particularly noteworthy, as it underscores the country's dominance in the battery sector and its determination to stay ahead of global competitors. A key example of this new technology in use is Huawei's IEO EV line. The ITO M6, produced through a joint venture between Huawei and Series, will feature CL sodium-containing battery pack. This joint brand, operational since 2021, combines Series manufacturing expertise and platform design with Huawei's software and components. Vehicles equipped with these sodium-ion batteries are expected to enter the market soon, bringing cutting-edge charging technology to consumers. The capabilities of these batteries are particularly striking. A slide from a recent presentation highlighted the 12C charging feature, meaning that a battery could theoretically achieve a full charge in as little as 3 to 4 minutes. Such speeds represent a breakthrough comparable to the leap from dial-up internet to high-speed broadband, setting a new benchmark for energy storage systems. Two configurations of the vehicle are planned, one using a sodium-based URV battery, and another fully electric model utilizing CL's advanced GIN battery pack. The GILN battery pack, also known as the CTP Celtoac 3, is CL's third-generation Celtopack design. This pack achieves an energy density similar to Tesla's 4,680 cylindrical cells at approximately 255 watts per kg. What sets the GILN pack apart is CL's claim that it can fit more cells per unit compared to Tesla's design, potentially increasing the vehicle's overall range. Early reports suggest that vehicles equipped with the GILN battery pack could achieve ranges of up to 10 kilometers on a single charge, making range anxiety virtually obsolete for most drivers. There is also mention of a condensed sodium battery featuring MP20 thermoelect electric separation technology. This condensed battery is said to have an energy density of 450 Wh per kg, which is substantially higher than standard lithium-ion cells. A battery of this caliber, with an 80 kilowatt-hour capacity, could provide over 800 meters, or roughly 300 kilometers of driving range. While these condensed batteries are not yet widely deployed in consumer vehicles, their introduction would represent a seismic shift in electric vehicle performance. Perhaps the most revolutionary aspect of this technology is the 12C charging capability. A 100 kilowatt-hour battery pack capable of handling 1.2 megawatts of power could be fully charged in under 10 minutes. This rate of energy transfer is virtually unprecedented and would require significant advancements in charging infrastructure. From power grid enhancements to new cooling and cable technologies, the Shun-YNC battery, the latest innovation from CL, is a testament to the company's relentless pursuit of progress. The first generation of Shun-YNC was already considered one of the most advanced lithium iron phosphate batteries in the world, but the second generation pushes beyond even that reputation. With the ability to exceed 1.3 MW in charging speed, it challenges the capabilities of any battery currently on the market, including those from leading Western manufacturers. This rapid development raises questions about infrastructure readiness. Charging stations capable of delivering such massive power levels are not yet widespread. Most high-speed chargers today max out at 350 kilowatts, a fraction of what these new batteries can handle. The industry will need to adapt quickly to make full use of these capabilities. Innovations in grid technology, energy storage, and thermal management will all be necessary to support the shift to ultra-fast charging. The implications go beyond passenger vehicles. Batteries with these characteristics could revolutionize freight and logistics. Electric trucks, buses, and heavy machinery. Sectors where charging time and energy density are critical stand to benefit immensely from sodium-ion technology. The ability to recharge large battery packs in minutes rather than hours could make electric freight vehicles as efficient as their diesel counterparts while reducing operating costs. Additionally, the advantages of sodium-ion batteries extend to grid storage solutions. Their fast charge-discharge cycles, low cost, and tolerance for temperature extremes make them ideal for stabilizing renewable energy sources like wind and solar. As a world transitions toward a low-carbon future, affordable large-scale energy storage will be critical, and sodium batteries are well positioned to fill that role. The next few years will determine how quickly sodium-ion technology can be scaled for mass adoption. CATL has signaled that these advanced batteries will begin appearing in electric vehicles within the next 6 months. If this timeline holds true, it will be one of the fastest commercial rollouts of a new battery technology in history. The combination of rapid charging, high range, and lower cost will make these vehicles highly competitive and could reshape consumer expectations worldwide. International competition is certain to intensify. Companies in South Korea, Japan, Europe, and the United States will need to accelerate their research and development efforts to keep up with the pace set by China. The groundbreaking unveiling of CATL's next-generation sodium-ion battery technology represents far more than just another incremental advancement in energy storage. It heralds a fundamental paradigm shift that could completely reshape the global clean energy landscape. As competing manufacturers scramble to respond to this technological leap, we're likely to witness an unprecedented wave of strategic alliances, cross-border licensing agreements, and revolutionary manufacturing processes emerging across the industry. Established battery giants and ambitious startups alike will be forced to fundamentally rethink their R&D roadmaps and production strategies as they attempt to bridge the growing technological gap with China's battery leaders. This disruptive innovation doesn't merely improve upon existing lithium-ion technology, it challenges the very foundations of current energy storage paradigms by delivering what was previously considered impossible. Ultra-fast charging capabilities exceeding 200 kilowatts or 12 C rates that could enable full vehicle charges in mere minutes rather than hours, while simultaneously achieving energy densities that rival premium lithium cells at potentially game-changing lower costs. The implications extend far beyond just faster charging electric vehicles. We're looking at the potential democratization of clean transportation through dramatically reduced battery costs, the elimination of range anxiety through both extended driving distances and rapid recharge capabilities, and the opening of entirely new applications for electric propulsion in sectors like heavy freight, aviation, and marine transport that were previously considered impractical due to energy storage limitations. Moreover, the inherent advantages of sodium-ion chemistry, including superior performance in extreme temperatures, enhanced safety characteristics, and the abundance of raw materials, position this technology as a cornerstone for the coming renewable energy revolution, capable of stabilizing power grids increasingly dependent on intermittent wind and solar generation. What makes CATL's breakthrough particularly transformative is its timing, arriving just as global markets are reaching inflection points in EV adoption and renewable energy deployment, meaning this technology could rapidly become the new standard rather than merely an alternative option. The convergence of these technical capabilities with growing environmental imperatives and shifting consumer expectations creates perfect conditions for mass adoption, potentially accelerating the global transition away from fossil fuels by several years. This isn't simply about better batteries. It's about enabling an entirely new energy ecosystem where clean, affordable, and convenient power becomes universally accessible, fundamentally altering how we think about transportation, energy storage, and our relationship with technology in a carbon-constrained world. The true significance of this technological breakthrough extends far beyond the impressive technical specifications of 200 kilowatt charging speeds or energy densities, rivaling lithium-ion cells. It represents a fundamental reimagining of what's possible in our global energy future. When future historians look back on this pivotal moment in energy storage technology, they may well identify it as the turning point that accelerated the clean energy transition from theoretical possibility to practical inevitability. This innovation challenges long-held assumptions about the limitations of battery technology, effectively rewriting the rulebook for what society can expect from energy storage solutions. The implications ripple outward across multiple dimensions. It redefines consumer expectations about electric vehicle convenience, potentially making charging times comparable to traditional refueling while offering superior range. It transforms the economic calculus of renewable energy integration by providing affordable, large-scale storage solutions. And it opens new frontiers in sectors, ranging from grid stabilization to industrial applications that were previously constrained by energy storage limitations. Perhaps most profoundly, this breakthrough serves as a powerful demonstration of how technological leaps can reshape entire industries almost overnight, forcing competitors to either innovate rapidly or risk obsolescence. The benchmark being set today will likely catalyze a new wave of research and development across material science, manufacturing processes, and energy system design that could yield unexpected breakthroughs in adjacent fields. As this technology matures and scales, it may well become the foundation for energy solutions we haven't even imagined yet. From fully electrified transportation networks to decentralized microgrids in developing regions. The true legacy of this advancement may ultimately be measured not just in its direct applications, but in how it expands humanity's collective imagination about what's achievable in the clean energy transition, inspiring a new generation of innovators to pursue solutions to challenges we currently consider insurmountable. In this sense, the most valuable output of this breakthrough may not be the batteries themselves, but the paradigm shift they represent, proving that with sufficient ingenuity and determination, even the most entrenched technological barriers can be overcome to create a more sustainable energy future.